Throughout the majority of calculus, the derivative is thought to be the instantaneous rate of change, or the slope of a tangent line to a curve. But these are not good enough to describe what a derivative really tells you. The derivative shows the rate at which a function changes. How fast does a function increase or decrease when x is slightly nudged? Basically, the derivative is a measure of how sensitive a function is to changes in x. It is much easier to show this with a geometric view. I will use the function x squared since it can very easily be transformed into a shape, a square with side lengths of x. Now, the change in the function is the same thing as the change in the area of our square. Now we are trying to use this square to build the function's derivative. So let's label what proper derivative notation is at the top. Again, the derivative asks the question, how sensitive is the function to changes in x? So let's change this function, change x, by some tiny deviation in x, which we'll call d of x or dx. This demo will make dx much larger than it should be, so remember that. It will come in later. As we increase x by dx, the area of the function increases by these green rectangles. This change in the area is the deviation in the function, represented by our variable d of f, or df. Let's plug in the areas of these rectangles now. The two long rectangles are both x times dx, and the small square is dx times dx, or dx squared. Now, we combine like terms to clean this up. Now, we'll divide a dx out of both terms, something I like to call reverse distribution. Now we'll divide both sides by dx so that we can model our equation on what proper derivative notation looks like, the green equation at the top. Remind yourself that dx is some really small number, close to 0. This is probably more like what the real dx would be. So if any terms with dx remain after the equation has been put into derivative notation, they can be erased, because the term is so small it is negligible overall. This leaves us with the finished differentiation, the finished derivative of x squared, 2x. What this 2x means is that the rate at which the function changes, in other words, the speed at which this function gets larger, is increasing by 2 times x for every change in x. I actually encourage you to try this same tactic, but for x cubed, since x cubed can just become a cube with side lengths of x. The next segment shows x cubed's derivative, so try and use this strategy to find the derivative before I show it to you. If we compared the derivatives of x squared and x cubed, which is 3x squared, it means that x squared is much less sensitive to change than x cubed is. This is because if I plugged in any number for x in both derivatives, x cubed's derivative will always be larger than x squared's in magnitude. Again, this is because the derivative measures the sensitivity of a function, the rate at which it changes.